everyone. My name is Brian Gadraki. On behalf of my co-authors, Babaka Menazad, Najma Miramakani, and Nick Nikiforakis, today I'll be presenting our work titled The Droid is in the Details, Environment-aware Evasion of Android Sandboxes. Today, it seems like there are more and more cases of Android malware affecting 50 to 100,000 users or even more. What's more, this malware is not originating from shady side-loading sites, but rather the Google Play Store and other trusted markets as well. So the question arises, how is this malware able to get around the sophisticated dynamic analysis environments that are in place by these markets to prevent situations such as this? Well, any malware that can identify its presence in a sandbox can masquerade as a benign application in order to pass dynamic analysis checks. Now, prior work has looked into so-called red pills, which are static API values that betray the presence of sandboxes. Some examples of these are pre-initialized environment values. So, for example, contact books that are full of predetermined names and numbers, as well as static IMEI values that are the same for any instance of a particular sandbox. Also, static device sensor readings, so sensors such as GPS sensors and accelerometers that will always return the same exact value no matter how many times the malware or user application requests readings from that sensor. And lastly, VM-specific system properties, such as kernel modules that are loaded only when a particular real device is running. And then these kernel modules are then missing when running in a sandbox environment. So these red pills are very useful for attackers to determine the presence of a sandbox, but we also have solutions to these problems. So for example, using real and varying data in place of these pre-initialized values will prevent an attacker from fingerprinting those values. Also, using sensor simulation libraries to provide dynamic and realistic readings for particular sensors. And lastly, using bare metal sandboxes in place of emulators will prevent a lot of these VM-specific and static device sensor reading issues that sandboxes have. So if we have solutions to these problems, how is it that malware today is still able to get around these analysis checks? Well, to answer that question, I have a couple of examples. So here, you are the malware. Between these two screenshots here, you have to decide which one is the sandbox and which one is the real device. And I promise this isn't a trick question. The answer is obvious here. It's the one on the right is the real device, where we could see that the user downloaded a number of applications that they're interested in that aren't pre-installed. And they also have a calendar widget here with a number of calendar events and reminders that are really only there when a real user is actually interfacing with this device on a daily basis. While the one on the left is just a clean installation of Android. There's no sign of a user actually using this device. Now, the second example is a bit more obvious, but a bit more abstract. So here, we're imagining a piece of malware is supposedly running on a Google Pixel. Now, if the malware is running on the device on the right, and they know that a Google Pixel has a camera sensor and a fingerprint sensor, it'll be quite odd to request a heartbeat from one of these sensors to know that the sensor is there and realize that they're not. So unlike a traditional desktop environment where a user can customize different hardware modules and plug in a new graphics card or whatever they feel that they need, on a mobile device, this is impossible. The actual hardware is locked down. So a Google Pixel will always have a camera and will always have a fingerprint sensor. So if there's a case where these don't exist, that raises some red flags for malware. So without even thinking about it, by making these determinations, we were using what is called environment-aware sandbox detection. So rather than relying on any one particular feature, we as people who have used smartphones for the past decade plus have learned what a real Android device environment feels like overall. So in this work, we are able to create a machine learning model to do this sort of learning of the Android environment using three main artifact categories. So first we look at wear and tear artifacts. which are artifacts that paint the picture that there was a real user actually using this device. So that includes the number of photos on the device, the number of songs on the device, the number of calendars and Wi-Fi networks, and so on. We also look at device configuration artifacts. So these are artifacts that show that a real user was actually configuring particular options within the device, such as the screen brightness or sound levels. These are types of options that a user will slide on a slider within the settings application to some continuous value. If we find that there's the device has the sound levels at exactly 50%, that's a little bit too artificial. And lastly, we look at device hardware artifacts. So this is like the second example from a few slides ago. We're looking at the total number of sensors available to each particular device, and also which sensors are actually available and can be interfaced with by the application. So we want to collect these artifacts on a large number of devices. So to do that, we created a data collection agent, which is just simply an Android application that uses the Android API to collect these artifacts and transmit them to our servers over HTTPS. So on the right there, you can see a screenshot from the application that users would see. So using this agent, we ran 3 different data collection exercises. So the first was a user study for which we obtained an IRB approval, and we collected data from over 1,200 devices from members of our university, as well as workers on the MicroWorkers crowdsourcing platform. Next, we got data on almost 400 freshly installed devices from Google Firebase and Amazon Device Farm. So these are devices that, unlike the user study devices, where it's a user's personal device that they added wear to the device and allow us to collect these wear and tear artifacts, we also wanted to look at a baseline device fresh out of the box. In the case that a sandbox provider will use a fresh device, a real device, to use as a sandbox. And then lastly, we collected data from actual sandbox providers. So there was about 200 of them. And these include app marketplaces. So the Google Play Store, for example, when you submit an application to the Google Play Store, it will run through one of these sandboxes. We also look at academic sandboxes from prior work, and also commercial malware detection services. So after collecting all of this data, we could see right away that so here's a subset of all the artifacts. These are just the wear and tear artifacts, but if you're interested, you could take a look at our paper. We have other figures showing all of the artifacts. But here you can see that there's a subset of artifacts that have a lot more identification power than others, and some are more surprising. So we could see that artifacts such as the number of contacts and photos and the average photo orientation, we could see that the real devices have a much larger value for all of those, which allow us to distinguish between the two. However, we have artifacts such as the number of processes, which it's actually much lower on real devices than what we expected. We expected kind of something along the lines of with the photos and contacts. But we theorize that this is mostly due to some of these baseline devices and these sandbox devices having a large number of processes running for, say, data collection and so on. So using this data and using these artifacts, we train a gradient boosted decision tree forest. And we train on data that is balanced between one set of real user devices and the other class being the baseline and sandbox devices. So in this case, we consider these baseline devices to be sandboxes in order to cover for the case where a sandbox would use a freshly installed physical device as a sandbox. So in total, we achieved an accuracy of 98.54 in distinguishing between these real user devices and the sandbox class. We also have a very low false positive rate and only 1 false negative rate. So in the case of sandbox detection and evasion, a false negative is a lot more costly than a false positive. So a false positive would mean that the malware thought that a real device was a sandbox and just didn't run the malicious payload. From the perspective of an attacker, that's okay, because if we're just missing one victim out of the thousands or hundreds of thousands, that's okay. But labeling a sandbox as a real device could be disastrous, because then the malware will be found out and removed from the PlayStore. So one false negative is a very good result. We also look at the robustness of our classifier. So we wanted to make sure that a sandbox provider can't simply just patch, the first 5 most important artifacts and completely, bypass our classifier. So what we did is we ranked all of our features by their importance to our classifier and iteratively removed the most important one, retrained and retested. And what we found is that there really isn't a drop off in performance until we remove 75% or more of the actual features. So what this shows is that our classifier is really learning the entire Android device environment overall, as opposed to just relying on a few very important features. On top of creating this general classifier that distinguishes between real devices and sandboxes, we also wanted to see if we could create device vendor specific classifiers, which would pretty much mean that we train on a subset of device specific artifacts that paint the picture of what a Samsung device looks like or what an LG device looks like. So we created one classifier per vendor, and we created gradient boosted decision trees again, but this time we trained on a balanced data set between baseline devices and sandbox devices. And then we could compare the vendor reported by the device using the Android API with the classifier output, with the idea being that if the device says that it's a Samsung device, for example, and then we use the Samsung classifier on the data from that device, if the classifier says this is not a Samsung device, then we know that there's some sort of a discrepancy there, and this could be a sandbox that's just pretending to be a Samsung device. So what we found is that sandbox devices don't look like the real devices that they claim to be. So the distributions of the artifacts from sandbox data does not align with the real devices of the same vendor. So what we see in the figure on the right is on the top, our device-specific or vendor-specific classifiers rather perform much better on real device data than they do on sandbox data. And what this means is that the device is effectively lying about its make in a lot of the cases. And what we did is we used these classifiers to these discrepancies with these classifiers to correct false negatives. And so the one false negative that we had from our main classifier was corrected by using these classifiers here. So overall, we showed that there's, that these environment-based invasion tactics are very effective against current sandboxes. So what are the countermeasures? Well, sandbox providers can simply use real Android devices as opposed to emulators. This will prevent all hardware-based fingerprinting that we showed. However, if emulators are necessary, the emulators can simply return artificial values for system APIs that were taken from realistic distributions. So collecting data from real devices would allow these emulators to then return realistic values for this data when a piece of malware asks for it. However, this is a fool's errand, as there could always be a new API endpoint that the malware uses that is not covered by the emulator. On top of this, it's really important for sandbox providers to break in the devices that they use as sandboxes. So to do this, they can simply clone a real user's device in order to get all of the wear and tear artifacts and device configuration artifacts set to look like a real user, or also try to impose some artificial wear on the device using some maybe automated usage tools. But again, it's very hard to make artificial wear look real. So it remains to be seen if that's actually something that can be used to bypass classifiers like ours. So in conclusion, we presented device environment-based evasion of Android sandboxes. We demonstrated that they're highly effective against popular Android malware analysis engines. And we also investigated the efficacy of using vendor-specific models to further assist sandbox evasion. So the main idea is that sandbox providers can't simply just patch one or a small number of red pill API endpoints. They must be able to emulate the entire Android environment. So all data and machine learning models that we created in this work are available at the URL listed there, droidindedetails.github.io. Thank you for your time, and I'd be happy to take any questions.